right, we're ready to get back to PChem. So today is, technically speaking, the threshold between our first half of the quarter and the second half of the quarter, right? So our first half of the quarter is pretty theoretical, I would say. We start from ideal gas equation of state, discuss first and second laws of thermodynamics, and then define what is material equilibrium, also Helmholtz energy, Gibbs free energy, how are they defined? And then in our last lecture, we introduced material equilibrium and the concept of chemical potential. Right? So as a quick review, if you remember, our chemical potential is defined to be this mu for species I in phase alpha as a function of temperature in phase alpha, pressure in phase alpha, species N1 in phase alpha, species N2 in phase alpha, etc., etc. So that's the definition of our chemical potential to be equal to the partial differential of your Gibbs free energy in phase alpha. So note that this is the total Gibbs free energy of everything in your phase alpha over the change of number of mole of your species alpha at constant T, P, and your N equals to J. Right, so before we move on, I want to make sure we're on the same page when we're talking about chemical potential. Like in a typical reaction, let's imagine if we have A plus B goes to C plus D. Actually, add the coefficient. Or alternatively, you can write this as 0 goes to negative AA minus BB plus CC plus DD. All right, and let's say in here, my A is in phase alpha, B is in phase alpha, C is in phase alpha, and D is in phase beta. So in this kind of reaction, the chemical potential of your species A in phase alpha will be equal to the partial differential of your Gibbs free energy in phase alpha over the NA in phase alpha while keeping T, P, your B, C, and D all as constant. And now in here, what is my DG alpha? My DG alpha here equals to your GA in phase alpha plus GB in phase alpha plus GC in phase alpha. All right, so that's a quick refreshment of your memory in how do we define Gibbs free energy. And then from the definition of the Gibbs free energy in our last lecture, at the end of our last lecture, well, of course, we went over the phase transfer, whereas what exactly is chemical potential. Remember, in phase transfer, the magnitude or the relative sign or relative magnitude of your chemical potential tells you what's the direction of your substance flow, right? So that's in phase transfer. But in our last lecture, we also went over reaction equilibrium, so that for this kind of general reaction of 0 goes to the sum of your stoichiometric coefficient times your chemical species AI, we have my DNI, so the number of mole of each species equals to the stoichiometric coefficient times the extent of reaction. All right, and for that extent of reaction, we know that at equilibrium, my dg Tp over d phi equals to the sum of your mu I and I. Or at equilibrium, your sum of your mu I equals to 0. So at equilibrium, the product, the sum of that product of your chemical potential times stoichiometric coefficient equals to 0. Now, what else do we know from here? If we move the term around, we got dg Tp equals to the sum of your chemical potential times stoichiometric coefficient times the infinitesimal change of your reaction, extent of reaction C. Or the other way to put it is my delta G at constant Tp is thus directly related to tell us what's the direction of our reaction, or what is the extent of our reaction. All right. So this is the link we're trying to make. It's the reason we care about the Gibbs free energy of the reaction is that knowing the Gibbs free energy of my reaction tells me information regarding where does the equilibrium shift. So as a preview on our future 2 chapters, in this chapter 5, we'll spend a good enough of time of talking about how do we calculate delta G. Or in this case, since we're specifying delta G at constant Tp, we're talking about how to calculate the standard Gibbs free energy of a reaction at certain temperature and pressure. And to do that, we'll be talking about using the appendix thermodynamic table. That's 1, use the thermodynamic table. And then 2, knowing where the number comes from. So let me find a thermodynamic table for you. Okay, so here we go. That's our textbook. 1 second. Bookmarked. Okay. So this is what your thermodynamic table looks like. So for your chemical species, we'll have our heat of formation or standard enthalpy of formation, delta H naught 298. And as we were saying, this appendix table is at constant temperature, constant pressure, right? And we have your standard heat of formation. You have your Gibbs free energy, standard Gibbs free energy of formation. We have the conventional molar entropy and also your molar heat capacities. So in this lecture, we'll be focusing on your standard heat of formation. So talking about how to use the standard heat of formation to calculate the delta H naught of the reaction. We'll also spend a good enough amount of time talking about where this number comes from. Or AKA, it's nice to read this table, but this number comes from actual experiments from physical chemists, right? So we'll spend our time talking about how physical chemists actually measure this number by setting up certain experiments. And then talking about, okay, so how does the delta H or the temperature dependence of your reaction heat in a certain chemical reaction. So that's our goal for today. It's a little bit ambitious, but if I'm behind, that's okay. I'm actually 1 lecture ahead of time, which I'm surprised to find, but I'll try to go slower now. Okay. And then in our next lecture, we'll be focusing on the conventional entropy of the reaction or of a species, and also the 3rd law of thermodynamics. And now if we know delta H, we know delta S, well, obviously we have a way to express the Gibbs free energy of formation of a certain species. All right, so that's the general structure of our entire chapter 5. We'll be going over around the table, the thermodynamic table. So my expectation to you is to know how to use the thermodynamic table like you were in Gen Chem classes, but just a little bit more well-defined. And 2, knowing where these numbers come from. All right. And in our next chapter, which is lecture 17, we'll start to talk about actual ideal gas reactions and taking everything together. But this is just a general preview on where we are. Okay, so back to today. We are at chapter 16. All right. So as we were saying, We'll start by looking at delta H. So today we'll focus on enthalpy. Now, in that table, you already see we have standard state. So here is a quick definition of standard state. So when we say a standard state, depending on the phase of that substance, for any pure substance that's in solid or liquid form, the standard state always refer to pressure equals to 1 bar. So if we look at this delta H naught, 298 Kelvin, so this little naught tells me my pressure is at 1 bar, right? So that little naught tells me my pressure is at 1 bar. And this temperature is 298 Kelvin for our appendix table. It could be different in other version of thermodynamic table, but nevertheless, the standard state just require a certain temperature. Doesn't need to be 298 Kelvin, but must be a defined temperature. That's for solid and for liquid. For gases, we have one more criteria. So the standard state of a gas will be the gas behave ideally. And we'll discuss solution if we got enough time. It looks like very good. So if we got enough time, we'll discuss solution and the standard state of solution in later chapters. All right, so far so good. So you'll see these kind of questions in true and false problems. Like for example, we could ask you a true and false problem to say the standard state of a ethanol gas must be ideal. So that's true, right? And at 1 bar something. Nevertheless, so that's a definition of standard state. Next go, the standard enthalpy of reaction and how to calculate the standard enthalpy of reaction from the table. So again, we have this general reaction, AA plus BB equal to CC plus DD. In general, when we're calculating delta H naught of a reaction, it's product minus reactant, right? So in this case, what do we have? First, we have all these coefficients. So these are my stoichiometric coefficients. So positive for product, negative for reactant. And in here, we have the standard enthalpy of each species, or standard molar enthalpy of each chemical species. For any kind of reaction, this is always true. So on the right-hand side, these are my reactants. And my products. Or if we want to write it in a general format, so for any kind of reaction where it's 0 goes to the sum of stoichiometric coefficient times chemical species AI, your H naught at certain temperature equals to the sum of your stoichiometric coefficient times the molar enthalpy of species I at certain temperature. So far, so good. Very straightforward. All right. And now we're trying to make a link between what we see in the table. Like, for example, how do we know what is the molar enthalpy of each of my species? So that goes to the definition of a standard enthalpy of formation. So these are the things in your appendix table. Right, so these are the delta H naught of formation you'll read from your thermodynamic table. Or by definition, the standard enthalpy of formation is saying the enthalpy change when 1 mole of pure substance, whatever that substance is formed from its elements in relevant form. So if we use graphite as our, well, if you use formaldehyde as an example. So the question here is like, how do we form formaldehyde gas from its elemental form? So what we're saying is the elemental form of your carbon is carbon graphite solid. Your elemental form for H2 is your gas phase. and your oxygen. It goes to form your formaldehyde. Or when we're talking about using the thermodynamics table, what are we saying? Is using the standard enthalpy of formation, we can quickly calculate the standard enthalpy of a reaction. So likewise, again, when we're talking about the change of enthalpy, remember our change of enthalpy is always a state function, right? So it doesn't matter how do we go from my reactant to product. So in this case, what we want is my WOM, which is the enthalpy change between your AA to BB, go to CC to DD. But what we can do is to break down your AB, your reactant A and B into your element, your reactant C and D into its element. So what does that mean? So if we focus on process B, what do we have? It's a delta H naught of your process 2 equals to the element in their standard state. So the element in their standard state, these will have delta H equals to 0. Let me see. So in this case, if we're breaking that down, your delta H naught will be negative A, the heat of formation of your reactant A, minus B times the heat of formation of your reactant B. And to form your product C and D from their elemental form, we then have your delta H naught T for process 3 equals to C times the heat of formation of your product C plus D times the heat of formation of your product D. Or overall, if we add your 2 and 3 together, you get your process 1, which is the one we're looking for, and that equals to, or your process 1 equals to your delta H naught 2 plus delta H naught 3. And we end up getting my overall reaction equals to the sum of your stoichiometric coefficient times the heat of formation of your each species. Again, it's more like GenChem, but break it down into more physical chemistry setup. Product minus reactant. How are we feeling so far? No questions? Okay, sounds good. So for these kind of questions, the application or the example question is pretty straightforward. We can just look at it together. Let's say, use the appendix data to find the delta H naught 298. So this is a delta H, a standard enthalpy of the reaction at 298 Kelvin for the combustion of 1 mole of sucrose, which structure is given as C12H22O11, to CO2 and H2O, right? So I'm listing the heat of formation of each species involved in this reaction. So for these kind of questions, it's very straightforward. You first write the balanced chemical reaction. So in this case, we're looking at the burning of your sucrose C12H22O11 in solid phase plus 12 oxygen gas goes to 12 CO2 gas plus 11 H2O liquid. If you already forgot how to do balancing chemical reaction, now it's a good timing to review your GenChem lectures and see how do you balance chemical reactions, all right? But then the question is asking for the heat of the standard enthalpy of the reaction at 298 Kelvin, so we can calculate that using our heat of formation. So we have delta H naught at 298 Kelvin equals to the sum of your stoichiometric coefficient times the heat of formation of each species. And in this case, we'll just plug in numbers. What do we have? Well, we have product minus reactant, so 12 times the heat of formation of CO2 plus 11 times heat of formation of H2O minus your reactant, which is the heat of formation of your C-sucrose. And your oxygen. Right, so in this question, I'm listing everything out for you, so it becomes just plugging numbers. But in reality, it's more likely you have to go to the appendix table and find each line. So the tricky thing here regarding using the appendix table is that you want to make sure you're looking at the correct phase. So for example, in this question, we're looking for CO2 in its gas phase. So you want to make sure you're searching for the correct line for the number. That's the biggest drawback. It's like, don't go too fast and get the incorrect phase. But nevertheless, from there, we end up getting the numbers plugged in. That's your 12 times negative 393.509 plus whatsoever. So yeah.
Why did you decide to write H2O in the liquid phase instead of gas?
Which thing?
In the
H2O?
reaction, yeah.
It should be in liquid phase, right? H2O is in liquid in 298 Kelvin.
Oh, at 298.
Yeah. So the reaction is asking you for the delta H at 298 Kelvin. So we do expect water to be a liquid at 298 Kelvin. All right, so you can try it yourself and plug in the numbers, and you can check your answer there. It's pretty straightforward. So this part is definition of standard state, and then how to use the thermodynamic table to find out the standard enthalpy of a chemical reaction. This part should be pretty straightforward. Next question. Remember, I expect you to know how to use the thermodynamic table, but at the same time, you also want to know where does this number comes from? Like, how come we know the heat of formation of these species? Like, how do they come from? If we use our heat of formation of like a gas, like a CO2 gas as an example, and let's see how the delta H is being measured, right? So now our goal is switching gear to talk about how are these numbers being experimentally measured. So I'm gonna go over with you like in a stepwise fashion. Now, if you think about the process, what do we have? In reality, what we have is a real gas, and the standard state of, let's say, a gas molecule here, we're talking about your pressure equals to 1 bar, temperature equals to, say, 298 Kelvin, and we should be good. But the tricky part here is for a gas, we say the standard state is ideal. So things can be a little bit complicated when we're transferring your real gas with ideal gases. All right, so how exactly can we do it? So the best thing we can think about is, let's say we start from a real gas. The first step here is somehow we convert your real gas into a hypothetical ideal gas. So this is the first question here. How do we interconvert your real gas with hypothetical ideal gases? So we'll put question mark here. That's our question 1. After we make the real gas into a hypothetical ideal gas, next question is, what is the delta H of mixing at your certain temperature and pressure? So keep in mind, we're talking about the formation of your species from its elementary form, right? So the actual reaction, for example, the formation of CO2, that's from your carbon, graphite, plus oxygen, gas. and into CO2 gas. Now this one is straightforward. It's like solid with a gas, but you can also have gas with gas or H2 and O2 to form water. But nevertheless, the question is, we're talking about the mixing at certain temperature and pressure equals to 1 bar. And now thinking about, we have this ideal gas, and this ideal gas, we can calculate the change of enthalpy at different temperature and pressure. So you can bring the temperature and pressure to different value for ideal gases. This is something we know how to calculate. And later on, we can measure delta H of the reaction in which the compound is formed from the mixed element. So we can think about this one to be, again, your carbon graphite plus oxygen go to CO2. And once the reaction is finished, we'll be able to go back and address the temperature pressure differences and go back to address ideal gas, real gas differences. All right, so that's the general strategy. So we'll start from the first one, which is talking about the measurement of delta H of a reaction when the compound is formed. Okay, so getting started, how are we measuring the actual heat of formation? So this is the experimental setup called calorimetry. So what do we have here? So this is a typical setup of a calorimetry. What do we have in here is a huge water tank. And in there, we have like a sample container. So outside is water bath, and we have the temperature of the water bath. And let's put my water bath as K. And inside you have a bomb, or where the reaction takes place. And for the bomb and the water bath together, they are thermally insulated with the rest of the universe. So these walls are adiabatic walls. All right, and in here, we have my reactant, like oxygen and some kind of product. What else do we know? Now, in here, again, we're talking about a chemical reaction, yes, but after all, we're measuring the differences of your thermodynamic state before the reaction takes place and after the reaction takes place. All right, so what does that mean? That means our initial state is my reactant. So in this case, let's imagine that's my carbon graphite plus oxygen gas and my water bath. So the total thing is kept as 298 Kelvin. After the bomb calorimetry is taking place, like we ignite our graphite in oxygen, and we get our product, and also our water bath K. And now we have a different temperature, which is 298 Kelvin plus delta T. So far, so good. What else do we know? We also know that for my entire system, considering my reactant, my bomb plus water bath, we have my delta U equals to Q plus W equals to. Now, in this case, my entire bomb and water bath are surrounded by the adiabatic wall. So if we come back here, so my bomb and my water bath are both surrounded by an adiabatic wall. So my Q equals to 0. Also, these walls are rigid, they don't move. So if we're considering both my water bath and my bomb together, my work also equals to 0 from rigid walls. Or the other way to put it is using our first law of thermodynamics, we can write my delta U equals to Q plus W equals to 0. All right. So what are we looking after? So remember, in this case, we're looking at the standard enthalpy of the reaction. Or the other way to put it is we want to get my product and my water bath at 298 Kelvin. Like this is an actual experiment. You start from reactant and water bath, you go to product and water bath at a different temperature, but in reality, we want it to be product plus water bath at 298 Kelvin. So what we're looking after is the change of this reaction. It's the difference between these two states. Or we get that to be, oh, I already write it out, to be the negative of the specific heat capacity, that's something you can measure, of your water bath and the bomb calorimeter. Times delta T. All right, so that's the amount of internal energy change for your reaction taking place. Yeah.
Why is there a negative sign?
So this is from here. If you think about these processes, we're talking about a change of C, K plus P times delta T, right? But the overall delta U equals to 0. So from here, from this initial state to my final state, if the temperature is not changing, we're talking about that process equals to 0. So this difference becomes the negative of what we want. So the simple question could be, we ask you to calculate, say, we have combustion of like 2.016 gram of your solid glucose at 25 degrees Celsius in this adiabatic bomb calorimeter, and we give you the heat capacity of the calorimeter and also a temperature rise, and ask you to calculate the delta U 298 of the standard delta U 298 at 298 Kelvin of your solid glucose. And this effectively tells me that's the delta U naught 298 of 1 mole of glucose. So that little c tells you that's the delta U naught of 1 mole of glucose. Yeah, the C subscription tells you that's for 1 mole of glucose. So this question then becomes a pretty straightforward one. First, we can calculate the delta U 298, the standard delta U 298 equals to negative C K plus P delta T, which is just plugging numbers. So my C K plus P is given here. My delta T is given here. So plugging the numbers to get the delta U of this 2 gram of glucose and then transfer it into 1 mole of glucose.
It seems 1 mole, not combustion.
This one in your textbook, I think I double checked. They say that's 1 mole, but maybe combustion. Let me double check and get back to you.
Formation is F.
Yeah, true. All right, so from here, from the bomb calorimetry, we got our internal energy measured. Next question comes is how do I translate that internal energy differences into delta H, into enthalpy differences? So in this case, again, the differences between your delta H naught and delta U naught, that goes back to the actual definition of H equals to U plus PV. So what else do we know? We also know my delta H naught equals to delta U naught plus P delta V naught, and know that we can do this because we specify that little naught specified my pressure equals to 1 bar. So my pressure is constant. I can take it out from the integral, and that's why we're simplify it. So this becomes a solved problem. We already know how to calculate delta V naught for different species. typically, your delta V naught is negligible for reactions not involving gases, like for only solid or liquid, it's negligible. For reaction involving gases, that's also a solved problem, right? So V naught, again, we're talking about the standard state of your gas, which are ideal gases. So in this case, since V naught is ideal, we got V naught equals to nRT divided by P naught. And we can simplify it to be delta H naught equals to delta U naught plus delta NG RT over P naught times P naught. These two cancel out. You get delta H naught equals to delta U naught plus delta NG times RT. R is a constant, T is a constant, but the number of mole of your reactant and product could be changing. So here, delta NG stands for the number of mole of your gas molecules. Since we're talking about ideal gases, then I don't really care about what exactly is the identity of my ideal gas molecule. It's more like how many number of mole of ideal gas molecules is different between your reactant and product. Like in this case, for example, in my reactant, we have 12 mole of gases. In my product, I also have 12 mole of gases. So the stoichiometric number is the same. So the delta G NG for this reaction would be 0. All right. And then we can have a typical kind of reaction. So let's say if we know the delta H formation of, this gas, which is CF2Cl, CF2Cl, and we're given the delta H of formation, and we're asking you to calculate the delta U of formation for the same gas. So to transferring between your delta H formation and delta U formation, you're counting the number of gas molecules in differences. So in this question, my delta NG, or the change of number of mole of gas molecules, in my product, that's 1. In my reactant, that's 3. Right, so, and this is the formation reaction of your molecule CF2, Cl, CF2Cl. Your delta NG equals to 1 minus 3 equals to minus 2. And then just plug in the numbers. And occasionally in physical chemistry, you might not be able to build these kind of reactions in a single bomb calorimeter. So that relates to our next goal, which is using Hess law to build the reaction we want from multiple reactions. All right, so this is the setup of your bomb calorimetry. Any questions before I move on? So next step is, what if we have multiple reactions we care about? We want to use multiple reactions to build the reaction we want. So this is called Hess law. In general, Hess law is say the overall enthalpy change for a reaction is equal to the sum of enthalpy changes for the individual steps in the reaction. So that's why you can add multiple reactions together. Like for example, if we have a Haber process, like a multiple step process, you start from H2 gas and N2 gas to form N2H4, and then from N2H4 reacting it with H2 to form NH3. So that's a two-step reactions. Now in here, we have these two are my reactants. Your N2H4 is my intermediate. And likewise, the N2H4 on the bottom is being consumed. That's why it's an intermediate. and then your NH2, NH3 is your product. Your H2 is also a reactant. So in this kind of example, we can write for the first step, delta H naught, or the standard enthalpy of reaction for my first reaction, equals to the product minus reactant. So delta H naught N2H4 minus your reactant, which is 2 delta H naught H2 plus delta H naught N2. And your second delta H naught 2 equals to product minus reactant again, so 2 delta H naught NH3 minus this intermediate and your reactant. So you can actually use the appendix table to do this calculation. If we do so, we'll get the first one being 95.4 kilojoule per mole. The reaction is endothermic. The second step is negative 187.6 kilojoule per mole. And the reaction is exothermic, releases heat. So first step absorbs heat, second step releases heat. The overall reaction thus becomes, we can cancel out some of them. Like for example, my intermediate will cancel out. So as a whole, we have 3 more of H2 reacting with 1 more of N2 to form 2 more of NH3. Or the overall reaction is, we can write delta H overall equals to delta H1 naught plus delta H2 naught, and that equals to product minus reactant. All right, and our overall reaction, you can calculate it to be negative 92.2 kilojoule per mole. So the overall reaction is exothermic. And this part, you can also put it onto the more straightforward energy profile version. So like what the reaction is happening is we start by having my delta H naught 1 to be uphill. And then your second one is downhill. By 187.6 kilojoule per mole. And the overall reaction is just the sum of these two. All right. So I left a practice problem for you to try it yourself. This part is, again, very straightforward. We're just talking about you can build your overall reaction from multiple elementary steps that we already know. Like the practice problem we have is, for example, we can ask you to calculate the standard enthalpy of hydrogenation of liquid benzene. So the first thing is you think about what is hydrogenation. So hydrogenation, we are adding hydrogen onto benzene to form C6H12 or cyclohexane, right? So how do we set it up? We can calculate it by looking at the standard enthalpy of combustion, standard enthalpy of combustion of liquid benzene, of liquid cyclohexane, and then looking at the standard enthalpy of formation of water, and then add them together to build our overall reaction. So this is a kind of example question you might encounter for this part of the lecture, which is Hess law. Actually, I have only 6 minutes, so I don't want to start a new topic. Let's just set this up and see what exactly do I mean. So for this question, we're saying the reaction we're trying to build here is a hydrogenation reaction. and looking at what do we have. Like, for example, we could say the standard enthalpy of combustion of liquid benzene. So that means you want to write out the actual reaction of each statement. Like, for example, when we say combustion of liquid benzene, we're saying C6H6 in liquid form plus oxygen goes to CO2 and H2O. Balance the reaction, we say that's 6, and that's 3, and naturally over my oxygen, that's 2/4, 15. And this is gas, liquid. Likewise, combustion of cyclohexene, you have C6H12 in liquid form plus oxygen goes to CO2 and H2O liquid. And balance up, this is going to be 6. I have 12 hydrogen, so that's 6 in front of my hydrogen. And looking at my oxygen, that's 12 plus 6. 12 plus 6, 18 divided by 2, that's 9 in front of my oxygen. And then the standard enthalpy for the formation of water. So this one is the elementary H2 plus elementary oxygen to give you water. Yeah.
So we stopped writing, I guess, the temperature subscript. Is that implicit in the standard conditions that we're at 25?
So this one, I just get really tired of writing it.
Okay.
It's, 298 Kelvin. All right, and in this kind of question, what we're trying to build is the overall reaction that we're looking after, which is this one. And you think about like how many of each reaction I want. So in this case, on the left-hand side, I have C6H6. On the right-hand side, I have C6H12. So if I keep these two as 1, we use the formation of water to balance up. So in that case, what do we have? Let me write the first one. So C6H6 plus 15 oxygen, 15/2 oxygen, goes to 6 CO2 and 3 H2O. And as a product, I have 6 CO2 plus 6 H2O goes to C6H12 plus 9 oxygen. Right, and in the middle, I have like H2, 3 H2 plus, I have H2 plus 1/2 oxygen goes to H2O. So the first thing I want to keep is these two I want to keep as they are, like not changing it. But in the process, I want to make sure like I'm only adding 3 more of hydrogen, and everything else should be my intermediate, means they should cancel out. Right, so that the overall reaction we're looking after is C6H6 plus 3 hydrogen goes to C6H12. So the only thing I should have in my here that's not canceling out are these 3 terms. And I must have a 3 in front of my H2, and hence I want to add a 3 in front of all my substances. And checking, are they canceling out with each other? So I have 6 CO2 cancel out with 6 CO2. I'm forming 6 H2O, they cancel out. And here, if we add this together, they cancel out with my 9 oxygen, so I'm happy. Right, so overall, when we're looking at how to calculate the delta H of my final reaction, I have my delta H naught for my first reaction to be some number. You have delta H naught for your second reaction. You have delta H naught for your third reaction. So overall, the final delta H naught for my overall reaction equals to delta H1 naught plus 3 times delta H naught 2 plus delta H naught 3. Because we have 3 in front of my second reaction. All right, and after all, you can always check and see if your reaction is balanced by adding things together again. So the Hess law is pretty straightforward, just like need you to use your previous knowledge in like how to write a balanced chemical reactions and how to link different reactions to a overall reaction. And when calculating the final delta H, keep in mind if you're using 3 of this reaction, you want to add that 3 in front of delta H2 naught. All right, so I'll pick up next lecture to finish up in like what exactly do we mean by measuring delta H of the standard heat of formation of a species. Remember, we have 6 different terms. We only went over the first one, which is the calorimetry. So in our next lecture, we'll pick up from there.